Hey guys, welcome back to General Chemistry. Today we are going to take those two-dimensional Lewis structures and we are going to lift them up into 3 dimensions. So we're going to talk about our 3-dimensional molecules. Framework is a theory called VSEPR. So predicting shapes. Here I've got 2 molecules. What do they have in common? Well, both of these molecules have 3 different atoms. Carbon dioxide's got 2 oxygens and a carbon. Water's got 2 hydrogens and an oxygen. So all things considered, you would imagine that these 2 would be similar compounds. But when I look at them, they are not at all. This is realistically how they're depicted. So I see that my carbon dioxide, CO2, is drawn as a straight line. And I see that my water, H2O, is drawn as kind of like a bent molecule. So why in the world are these drawn as 2 completely different molecules? The other thing to think about is the properties of these molecules. So carbon dioxide, at room temperature, it's a gas, right? And then water, at room temperature, it's a liquid. So these 2 compounds have vastly different chemistries, and that has everything to do with the structures that you see on the paper. So how do we know to draw one of these as a straight molecule and one of them is bent? We're going to use a theory called VSEPR. So VSEPR stands for valence shell electron pair repulsion. That's a lot of really big words. So let's break this down. I'm actually going to start at the end. I'm going to start at the beginning. So valence shell electron. Well, of course, the electrons that we're interested in here are the valence shell electrons because those are the only electrons that are available for bonding. We see electron pair. So we've talked about lone pairs. We've talked about bonding pairs. So being able to recognize and identify those is going to be important. And then we've got electron pair repulsion. So remember, these electrons are all negatively charged particles. When I try to put them in the same molecule, there is going to be some repulsion there, right? There is going to be some pushback. 2 negatively charged particles don't really want to be in the same area. So that repulsion or that pushing away from each other is going to dictate the shapes of our molecules. So valence shell electron, pair repulsion. So electron groups are repelled by one another. They don't want to be close to each other. Before we can talk about how these 3-dimensional shapes take form, we've got to talk about these electron pairs that are repulsed or repelled by one another. So first and foremost, we need to focus on central atoms. So anything that we deal with in this section is going to be the central atom. So here, our nitrogen is our central atom. If we come up here to the top, our carbon is the central atom. And if we come down here on the bottom, the oxygen is our central atom. So we always need to remember to focus in on the central atom. So what kinds of electron pairs or electron groups could be attached to that central atom? Well, the first thing we can have are lone pairs. Okay. So if I look at this nitrogen here, I would say, yep, it's got 1 lone pair and then some other stuff attached to it. If I come down here to this oxygen, I would say that it has 2 lone pairs attached to the central atom. And then if I come up here on the carbon, it has 0 lone pairs. The next electron group or pair that we need to keep an eye on are single bonds, right? So again, if I'm looking here at nitrogen at the central atom, we said it had 1 lone pair and it has 3 bonding groups. 1, 2, 3 bonding groups. Over here on the carbon, it's got 1, 2 bonding, and then our oxygen, remember, had 2 lone pairs, and now it's got 1, 2 bonding pairs. So single bonds we keep an eye on. And then the last thing is our multiple bonds. So our multiple bonds count as one thing. We don't separate those. We keep them together as kind of a package deal. So again, if I'm looking at this carbon, I would say that it has 1, 2, 3 bonding groups. So this counts just as an extra 1 there. So now that we can recognize lone pairs and bonding groups on the central atom, now we can start talking about shapes. So in this scenario, we've got our central atom is beryllium. And if I look at the things that are attached to beryllium, I see 1, 2 bonding groups. Those 2 bonding groups are going to want to get as far away from each other as they possibly can. So what's the biggest angle that they can put between themselves? Yeah, that angle is 180 degrees. So if there's only 2 bonding groups, we're going to put the biggest angle we can between them, and that angle is going to be 180 degrees. And we get a structure that's called linear. It's a straight line. The next one, so this is one that we saw in our first slide. So carbon is our central atom. And if we look at how many things are attached to carbon, we've got 1, 2, 3 bonding groups. With those 3 bonding groups, again, we want to put the largest angle between those 3. Little bit deceptive the way that it's drawn. So we're like, oh yeah, there's 180 degrees here. Perfect. But if we look between this oxygen and hydrogen, it's only a 90 degree. So what's the biggest angle that I could put between these 3 and that angle be even between all of them? Well, the biggest angle that I can put between them is 120 degrees. So this molecule here is going to be trigonal planar. So it's flat in that all of these atoms are in the same plane. Like if I were to lay this down on a table, it would lay flat. So that's the planar part of it. But it's trigonal in that it kind of forms a triangle here. Okay. So that's our trigonal planar, 3 electron groups. All right, so for this one, we're going to look at the electron groups. We've got our carbon as our central atom. And we've got 1, 2, 3, 4 things attached. So in 3 dimensions, what is the largest angle that I can put between each of those hydrogens? You may not know this right away. That's okay. But the largest angle would be 109.5. Okay. So this molecule is what we call tetrahedral. So if I look at these 3 hydrogens on the bottom, they're going to kind of sit up off the table, kind of like a pyramid. So there's some space underneath that carbon atom. That carbon is not touching the table. And then we got that little base of our pyramid. And then sticking up to the top here, we've got 1 more hydrogen going up. Okay. So with 4 electron groups attached to the central atom, we have what's called a tetrahedral shape. So those are the first 3. Linear, trigonal planar, tetrahedral. But up until this point, all of the molecules that I've showed you have bonding groups. When we have a lone pair, we have a little extra step, a little extra wrinkle that we have to talk about. So let's look at our ammonia, our NH3 molecule. So let's first hone in on the central atom, so nitrogen. How many electron groups are attached to nitrogen? So we have 1, 2, 3 bonding. And number 4 is that lone pair. So 4 things attached to that nitrogen. Well, remember 4 electron groups, that gave us a tetrahedral molecule. So that's going to be part of the story. So we would say that the electron geometry is tetrahedral. Electron geometry takes into account all the things that are attached to nitrogen. But when we depict these in a textbook, very often we don't depict the lone pair. It's there, it's taking up space, but we often don't depict the lone pair. So when there's a lone pair involved, we also have something called the molecular geometry. So the molecular geometry is going to be essentially hiding the lone pair. What does that molecule look like? So the molecular geometry for this guy is trigonal pyramidal. So again, we've got that kind of pyramid at the bottom. So the 3 hydrogens at the bottom, there's a little bit of space underneath that nitrogen atom. The trigonal pyramidal is certainly a result of tetrahedral, right? That kind of dictated those angles. But molecular geometry is what you often see depicted in textbooks. Okay. So many answers for this test, I'll say, draw the Lewis structure. What is the electron geometry? What is the molecular geometry? So you have to have an understanding of both. Another example of this would be water. So if I draw the Lewis structure for water, we've got oxygen in the middle. We've got a bonding group hydrogen, and then this oxygen has 2 lone pairs. So again, if we look at the total number of electron groups attached to that oxygen, it's again 4 electron groups, so tetrahedral. But if we were to draw the molecular geometry, so kind of hiding those lone pairs, we're going to get a geometry that's bent. So this angle right here is roughly 109.5, and the molecule is a bent molecule. So we'll come back to this in just a second. So looking at these, it's not something you're going to have to memorize. I recommend having this table in front of you as you take the next exam. So we can predict each of these molecular and electron geometries. So students often ignore this first category. It confuses them. And instead, they kind of focus in on bonding groups and lone pairs. Okay. So if we look down here, we use water as our example. That's the last one we looked at. Water had bonding groups. It had 2 bonding groups. And then water also had 2 lone pairs. So 2 bonding groups, 2 lone pairs. Now we just read this straight across left to right. So the electron geometry is tetrahedral. Molecular geometry is bent. So this table is going to be what helps you to determine electron and molecular geometries. Let me go back and talk about one more thing. So with these electron geometry and molecular geometry, these lone pairs actually take up more space than a bonding group would, okay? So if I look at a bonding group, here's the nuclei of one atom, maybe the oxygen. Here's the nuclei of the other atom, maybe the hydrogen. And when they're sharing those electrons, these electrons are, the space that they're taking up is kind of stretched out, right? So we're stretched out between the 2 nuclei. When we're talking about a lone pair, we only have 1 nucleus that they're attached to. And then those lone pairs take up a pretty large volume here. So it's kind of a squatty, fat area that these lone pairs take up. And it tends to actually be more volume or more space than a bonding pair. So what this does is it takes our ideal tetrahedral molecule, which has 109.5 on each angle. It takes that molecule and it kind of scooches in these bonding pairs. So my big fat lone pairs up here at the top and on the side push in or create some tension between the hydrogens. So the actual angle between those two is 104.5. It's a much smaller angle. And it just has to do with the lone pairs taking up extra space. So what you'll see is here, as you're predicting the geometries, it'll tell you what the approximate bond angles are. So without any lone pairs, we'd have 120 for our trigonal planar. And then when we add the lone pairs in, it's less than 120. So just acknowledging that strain that the lone pairs put on there. Okay. So that is the first half of VSEPR. Later on in the lecture series, there's actually a second half to this table. But this is going to give us a good place to start. This is kind of the ones that follow the rules, and then later on we'll talk about the exceptions to the rule. I hope you guys found this helpful.